5.4 is about applying rules of exponents and solving exponential equations and power equations. So we have this problem, and we're essentially dealing with y equals a times b to the x. We've dealt with problems like this before where it's growing at some percentage and we have some starting amount times a growth factor to a power. And we've also written it as u sub n equals the original value times 1 plus r to the n, or in banking terms, a equals p times 1 plus r to the t. A being the amount of money, p the principal or initial deposit, r is the interest rate, t is the time in years. The 1 plus r is the value of our base. It's 1 plus r because the account is growing by some percentage. In this problem, we start out with $500, and it says after 8 years, our money doubles. Now we solve. Divide by 500. Now the powers alone, so I'm going to raise it to the reciprocal power, 1/8. I'm left with 1 plus r equals 2 to the 1/8. Subtract 1 from both sides. R is equal to 2 to the 1/8 minus 1. So we go to the calculator, and you'll see the top calculation here, 2 to the 1/8 minus 1 is 0.0905. So 9.05% is the interest rate that we were making in this bank account. So now we have a pendulum that's being measured how far away it is from something. At rest, the pendulum is 1.25 meters from the motion sensor. So as it swings away, every 10 swings, the distance gets measured. So the initial release point is 2.35 meters. And then after 10 swings, the furthest it goes away from the sensor is 1.97, and so on. We want to find an equation that models this data. And it's helpful to look at a graph to determine whether or not we should use a linear equation or a geometric equation. And I have that plotted somewhere here. Here's a plot of those points, and you'll notice that the gap between them vertically is getting smaller and smaller and smaller, which means that we're going to use a geometric rule, y equals a times b to the x. Now normally, y equals a times b to the x, when it's decreasing like this, when it's decay, we're getting closer and closer and closer to 0. But in this problem, we're getting closer and closer and closer to something other than 0. And what we're actually getting closer and closer to is 1.25. The measurement would be when the pendulum essentially stops swinging. So we can incorporate that into our equation up here as y minus 1.25 equals. That's how we can describe a vertical shift, or we could add it on to the end over here. Now, A is usually the initial starting value, but that initial starting value, just like every other y value, had to get shifted the same way as this y value. So what I'm going to write here is y sub 1 minus 1.25. This start value got shifted the same way that every other point, every other y value got shifted on this graph. And then we don't know the base, and we're going to write x minus x1 because there probably was a horizontal shift that happened here also. And what we're now going to do is we're going to pick 2 points from our data to find us b. And I'm going to use the points 10, 1.97 and 60, 1.32. And what that allows me to do is I can plug in an x1, y1 and x and y. Plugging in those 4 values for these x's and y's allows me to only have b that I don't know. So I do 1.32 minus 1.25 equals 1.97 minus 1.25 times b to the 60 minus 10. And then I just have to solve for b. 0.07 equals 0.72 b to the 50. Divide by 0.72. B to the 50th. And I plug this into my calculator and then change it into a fraction. It's actually 7 over 72. You could write a decimal if you wanted. But now the powers by itself, I'm going to raise both sides up to the 1 over 50. And I find that b is equal to 0.9545. So my final equation that models this data is y minus 1.25 equals 0.72. I keep this number right there. I keep the y1 involved in the problem times 0.9545 x minus 10. I keep that x1 in the problem also. If you compare this to what was done in the book, the numbers are slightly different because they used a different pair of points. And it's not wrong, it's just slightly different, and that's okay.